Hello everyone, I'm Hushuang Zhang. I'm very happy to present our paper here. Its name is Mining API Constraints from Library and Client to Detect API Misuses. Let's look at what is API misuse first. When invoking APIs, programmers must follow their constraints to avoid API-related bugs, incorrect usages of APIs, or violations of API constraints is called API misuse. API constraints are defined in the API implementation code, namely library code, and client code using APIs should follow API constraints. API misuse can cause programming errors. API misuse detection can save debugging time of programmers and improve code quality. Here are 3 API misuses that violate 3 common types of API constraints. They are real misuses from MUbench dataset. The first one violates the condition checking constraint of API iterator. It calls method next without checking the condition has next. The second one violates the call order constraint of API data output stream. It does not call method close after calling the constructor method. The third one violates the exception handling constraint of API long. It does not handling number format exception when calling method parse long. In prior researches, researchers mine API constraints from various sources to detect API misuses. The first ones mine API constraints from client code. They assume that deviations from frequent usage patterns in client code are API misuses. However, as client code typically only occurs a small portion of API usages, they cause a low recall and precision in detecting API misuses. Besides, it is difficult to collect sufficient client code, especially for newly released APIs and less popular APIs. The second ones infer API constraints from API documents. They typically adopt NLP techniques and heuristic linguistic patterns to infer constraints. The limitation is that documents are not always high quality or up to date. The third ones infer API constraints from library code. Library code covers all API constraints and is informative. However, as library code analysis is challenging, existing static approaches can only infer simple constraints, like unordered call sets. The fourth ones infer API constraints from multiple of above sources, like the combination of client code and library code. But it only infers simple constraints like call sets, and have not yet made an application on misuse detection. In this paper, we focus on inferring from multiple sources. There are 3 challenging problems when mining comprehensive and correct constraints, which results in the low recall and precision of previous researches. The first challenging problem is comprehensiveness. Constraints from client code are only a small portion of real constraints that occur frequently. Our treatment is to cover occur infrequently constraints through mining from library code. Here are some motivating examples to illustrate above 3 challenging problems. As for the comprehensiveness problem, let's see an example of API iterator. From client code, we can only mine the occur frequently constraint we should check method has next returns true before calling method next. From the library code, we can infer another occur infrequently constraint we should call method next before calling method remove. The second challenging problem is informativeness. Constraints from client code only represent the consequences of satisfying constraints, so they lack sufficient information and result in the misjudgment of misuses. Our solution is adopting the fine semantic details of constraints from library code to accurately detect misuses. Constraints from library code have the precede or follow type of call order constraints. Here's an example of API print writer. We can infer a follow call order constraint we should call method close after calling method write. With the follow type, only calling method close without calling method write will not be wrongly detected as misuses. Constraints from library code also have the alternative relations between condition checking and exception handling constraints. Here's an example of API file input stream. We can infer the alternative relation of checking condition file.exists and handling file not found exception when calling the constructor method. Client only needs to satisfy one of alternative constraints. Considering alternative relations can reduce false positives. The third challenging problem is accuracy. Constraints from library code can lead to many false positives because there are various ways to use APIs, and it's hard to infer all accurate usages from library code. So we also mine constraints from client code, which represent common and accurate usages. Here's an example of API list. From library code, we can infer a condition checking constraint list.size greater than index before calling method list.getIndex. From client code, we can mine the common pattern in actual usage checking condition list.isempty before calling method list.getZero. It's another way to satisfy the constraint. But constraints from only library code will wrongly detected it as misuses. The purpose of our approach is to take advantage of both the comprehensiveness and informativeness of library-based constraints and the accuracy of client-based patterns. This figure shows an overview of our approach, which contains four main components. C. Extractor mines from client code. L. Extractor infers from library code. CL integrator combines the results from above two components to produce API constraints. CL detector detects API misuses violating above constraints. First, we employ API usage graph to represent API constraints or API usages, because graphs are more informative to encode usage elements, structures, and data dependencies. In an August, nodes represent data entities and usage actions. Data entities contain objects, values, and literals. And usage actions contain method calls, operators, and instructions. Edges represent control and data flow between nodes, and are categorized into 8 types. In C extractor component, we employ frequent subgraph mining algorithm in MU detect to mine constraints from client code. The key idea is that the frequency of an API usage implies the certainty of its correctness. After building August from client code, we start from call nodes of target APIs and Augusts, and then recursively extends to larger Augusts while ensuring enough frequent occurrences. Finally, it outputs frequent subgraphs as constraints from client code. As for the L extractor component, we present 8 strategies for inferring various types of constraints from library code. To infer condition checking constraints, we use 4 strategies. In strategy 1, we extract conditions following the assert keyword. We extract null checks on parameters by identifying the parameters of method objects.require non-null. We extract null checks on parameters from sentences in at param or at throws annotations in Javadoc. In strategy 2, we infer from trigger conditions of throw statements. In strategy 3, we manually define the parameter constraints for some frequent native methods. For example, we should check the condition index less than air.length before using air index. In strategy 4, we propagate condition checking through method calls within calling depth n. To infer exception handling constraints, we use 2 strategies. In strategy 5, we infer possible thrown exceptions by locating throw statements. Throws keywords? We also obtain exceptions by identifying the annotations like at throws. At exception in Javadoc. In strategy 6, we infer their alternative relations with condition checking in the process of strategy 2. Client code can choose to handle exceptions or check exception trigger conditions. To infer call order constraints, we use 2 strategies. In strategy 7, we infer from call graphs. We find precede or follow call orders for all called methods. And then we push the call orders back to target API methods. For example, since the array should be initialized before using, we can find the call order method 1 precede method 2, owing to method 3 invoking method 1 and method 4 invoking method 2. It's propagated along the call relation graph and become method 3 precede method 4. In strategy 8, we exploit 2 heuristic naming rules to infer call orders. The first one infers call orders about iterations like has next line precede next line for API iterator scanner and so on. The second one infers call orders about resource usages like write follow close for API data, output stream and so on. The CL integrator component combines constraints from library and client code to obtain comprehensive and informative constraints. First, we build August for constraint from library code. Second, we merge constraints from both sources. If constraints are overlapped, we deliver the fine semantic details of library-based constraints to client-based constraints. Finally, to improve the richness of constraint, we generate new constraints through replacing a subgraph with its alternative constraints. The CL detector component employs graph matching algorithm in MU detect to detect misuse with our inferred constraints. First, we represent the code under check as Augusts. Second, we determine a potential misuse if its August is a violation of a constraint and matches none of its alternative ones. In graph matching process, we integrate fine semantic details of constraints. Third, we rank potential misuses by suspicious score, calculated as follow. It involves the constraint support CS, initial weight of library constraints SL, violation support VS, and the distance from constraints VD. Finally, it outputs the top-ranked reported misuses. Next, we conduct several experiments to answer 3 questions. First, how effectively does our approach perform compared with the state-of-the-art detector MU detect? Second, how is the quality of constraints inferred from library source code? Third, how do the constraints mined from library and client contribute to the effectiveness of our approach? As for the dataset, we use MU Bench as the API misuse dataset. It contains 223 API misuses in 57 software projects. Besides, we select 106 Java APIs as our target APIs for constraint inferring, including the 65 APIs used in MU Bench and 68 Java APIs that occur frequently in Stack Overflow. For each target API, we collect top 20 client projects as client code that use the certain class the most on GitHub through BOA tool. For our Q1, we compare our API misuse detector against the state-of-the-art detection approach, MU detect, on the MU Bench dataset. We use the recall, precision and F1 score to measure the effectiveness of detectors. Where F1 score is the harmonic mean between recall and precision, we calculate the precision on 10 projects and manually examine top 20 detected misuses for each project. As the table shows, the recall precision and F1 score of our detector are all higher than the baseline MU detect. So, our detector is more effective than MU detect. It indicates that our detector can find more API misuses and reduce wrongly identified misuses, with relatively more comprehensive and accurate API constraints mined from both client and library code. For our Q2, we evaluate the quality of constraints from library code. We measure recall and accuracy of each type of constraints and take the average. We did not calculate recall of call order constraints, because all actual call order constraints of complicated classes are difficult to determine. We invite 2 programmers to independently examine the quality of constraints mined from library. The table shows that constraints inferred from library code achieve high accuracy and high recall in average. Hence, our strategies can infer relatively comprehensive and accurate constraints of high quality from library code, which are significant for API misuse detection. For our Q3, we conduct an abletion study to explore the contributions of C extractor and each strategy of L extractor. We analyze how many real API misuses in MU Bench are detected when a specific component or strategy is missing. In this table, all minus L extractor means omitting the L extractor. All minus C extractor means omitting the C extractor. All minus C extractor minus strategy X means omitting the C extractor and a certain strategy. The result shows that constraints from library and client code make non-negligible contributions, and they complement each other. The effectiveness of our detector is attributed to both the accuracy of client-based constraints and the comprehensiveness and informativeness of library-based constraints. In summary, this paper proposed a by-source API misuse detector. To the best of our knowledge, our approach is the first static API misuse detector whose constraints are mined from both client code and library code. Besides, we designed 3 strategies based on prior studies and 5 new strategies to infer more comprehensive constraints from library code. Finally, our tool and dataset are released. Thanks for listening. If you have any questions, please contact me via the email address.